The second part of Chapter 6 deals with enthalpy and calorimetry. Enthalpy is historically a very difficult concept to get across. Enthalpy, which is abbreviated with a capital H, refers to the flow of energy or the heat exchange at constant pressure when two systems are in contact. So it is the flow of energy. It is a state function, and if you remember from the previous video, a state function means that it doesn't matter what's happened before or what's going to happen after. All that matters, the enthalpy value only matters, only relates to the current condition. At constant pressure, the change in enthalpy is going to equal Q. Remember, Q from the past set of video was heat. If we're talking about delta H, that's the difference between the potential energies of the products and the reactants. So that's what the very bottom equation refers to there. Delta H equals the potential energies of the products in the reactants and the difference between the two. And this graph, I think, better shows what that equation is trying to get at. So if you looked at the reaction and how much energy is in it, if you have a reaction where the reactants are starting at much lower energy than the products, then the delta H is the difference in the energy between the reactants and the products. So let's look at an example problem. So if you had an equation that said consider the combustion of propane, and with the equation, and you're given a delta H for the overall reaction. And it says, assume that all the heat comes from the combustion of propane. Calculate delta H, in which 5 grams of propane is burned in excess oxygen at constant pressure. So you're given the overall change in energy for the reaction, and it wants to know what is delta H when you have 5 grams of propane. So how would you go about figuring this? Let's show you. This is a classic stoichiometry problem where you would say, all right, I'm going to start out with 5 grams of propane. I guess I'm hungry. And you know that in 1 mole of propane, you have 44 grams. And then you know that there are negative 2,221 kilojoules per mole of propane. If you were to solve all that out, you would see that the answer is negative 252 kilojoules. So again, this is basically a stoichiometry problem where you can use the overall delta H, which refers to kilojoules per mole, and you figure out how many moles do I have in the 5 grams that I was given, and convert that to the overall energy. So it's much like you would do with a problem where you were given the molar concentration. All right, next up is calorimetry, and this is the process of measuring heat based on observing a temperature change when a body absorbs or discharges energy as heat. We are going to be doing a calorimetry lab, which I think will really help with some of these concepts. But essentially, if 2 reactants at the same temperature are mixed and the resulting solution gets warmer, this means that the reaction taking place is exothermic. The converse of that is it's endothermic if the reaction cools the solution. There's a couple of terms that you need to be familiar with when it comes to calorimetry. One of them is specific heat capacity, and that's the energy required to raise the temperature of 1 gram of substance by 1 degree Celsius. You can also look at that equation like this. The specific heat is the quantity of heat that's transferred per grams of material and degrees of temperature change. Molar heat capacity is the same thing as specific heat, except that it refers to the energy required to raise the temperature of 1 mole by 1 degree Celsius, and they would have the following units. Coffee cup calorimetry is an experiment, a classic lab that is done to find the energy of a particular system. It uses a styrofoam cup, and the reactants begin at the same temperature, and you look for an overall change in temperature that is occurring. Then you can use a formula, which I will show you in a second, to figure out how much energy is released or absorbed. This is also called constant pressure calorimetry because the pressure is not changing within this reaction. All that's changing is there's some type of temperature change that occurs when the reactants react. So you have two reactants, they start at the same temperature, you mix them together and you measure the temperature change. We'll be doing a version of a lab that is a lot like this one. So the reaction for calorimetry, basically the energy released or the heat is going to equal C, which is the specific heat capacity times the mass of the solution in grams times the change in temperature. The specific heat at water in this liquid state is 4.184 joules per grams degrees Celsius, or 1 calorie per gram degrees Celsius. Water has one of the highest specific heats known, and this property is what makes life on Earth possible and helps to regulate the temperature of Earth year-round. You will definitely need to know the specific heat of water, which again is 4.184 joules per grams degrees Celsius. The equation looks like this: Q, the energy released, and a lot of times you'll see the mass given before the C, but it doesn't really matter. It equals mass times the specific heat capacity times the change in temperature. So, keeping that equation in mind, let's try a problem. You have 100 grams of a sample of water at 90 degrees Celsius is added to 100 grams sample of water at 10 degrees Celsius. So what this is saying, you have two different samples of water at two different temperatures. What will the final temperature of the water be? Will it be between 50 and 90 degrees Celsius? Will it be 50 degrees Celsius? Or will it be between 10 and 50 degrees Celsius? The correct answer for this problem is B. It'll be 50 degrees Celsius. Let me show you how you could figure that out. You have to keep in mind that energy released is going to equal energy absorbed. So you could set this equation to be equal to each other. The mass times the specific heat capacity times the change in the temperature for one of the solutions has to equal the negative of the mass times specific heat capacity times the change in temperature of the other solution. So with the specific problem that we have here, you have 100 grams times the specific heat of water times the final temperature minus 90. And what that means is one of the solutions started at 90 degrees Celsius and it's going to end at some final temperature, and you don't know what that final temperature is. So you can just put the T sub F to indicate the final temperature. That is going to equal 100 grams times the specific heat times whatever that final temperature is minus its initial temperature, which was 10 degrees Celsius. It doesn't really matter which side of this gets the negative sign, just that when you're setting these two things equal to each other, one of them has to have a negative sign because the heat released has to equal the heat absorbed. We can then simplify the problem because we can get rid of 100 grams on either side and the specific heat on either side, and now we have two equations which essentially deal with the change in temperature. So the change in temperature of one solution has to equal the change in temperature of the other solution. So we can do some simple algebra and eventually get to the fact that the final temperature would be 50. Let's try another. Now we have a 100 gram sample of 9 degrees Celsius is added to a 500 gram sample at 10 degrees Celsius. In this situation, what would the final temperature of water be? Why don't you pause it here and see if you can look back at the way that the other one was performed and see if you can get to the correct answer here. If you said that the final temperature would be between 10 and 50 degrees Celsius, you would be correct. How would you figure that out? Well, you would set up your equation like you did before. So you've got 100 grams times the specific heat times the change in temperature is going to equal 500 grams times the specific heat times the change in temperature. We can multiply and simplify as much as we can, and eventually we will get to 23.3 degrees as the final temperature. Here is another problem. Now we have a cup and we have 50 grams of water at 10 degrees Celsius, and we're adding a 50-gram iron ball at 9 degrees Celsius to the water. The specific heat of water is 4.18, and the specific heat of the iron ball is 0.45. How would you figure this out? Go ahead and pause it. If you said the correct answer was between 10 and 50 degrees C, you would be correct. How would you figure that out? Well, you could say 50 grams times the specific heat for iron times the change in temperature of the iron. And so it says it starts at 90, and we don't know what the final temperature is going to equal 50 grams from the water times specific heat in water times the temperature change in water. And if you were to multiply all that out, you would get 18 degrees Celsius. And that is the end of this section.